So extending on why do we care to factor polynomials into linear factors, it all boils down to us being able to find solutions of polynomial equations. So when we were asked in our past math courses to try to solve these sorts of equations analytically, sometimes the first thing we would try for ourselves would be to see if we have 4 terms, maybe we can try to factor by grouping. And so if you try to factor by grouping, you might notice like, okay, well, we could take an x squared, a GCF, out of the first 2 terms. So you would get negative 6x minus 17. But then when you try to take a GCF out of 63x minus 10, you kind of run into a dead end. And we weren't given these types of problems in our previous math courses because we didn't have a technique to approach this. So factoring by grouping ends up not working. And if it does, good. You have a little bit of a nicer time. So if factoring by grouping did not work, we extend it to what did we just learn? Well, we can try to factor using synthetic division. But there's a catch. In order for us to understand the factorization of this type of polynomial, we'd first have to understand what root we are dealing with. If we don't have a root, we need a little bit more information for us to even try this synthetic division. Well, lucky for us, we actually saw this example earlier. We ended up having the root. I think they had told us from a previous example. They told us that P of 2 equals 0. So that tells us that we have the root equals 2. And that tells us that our factor is x minus 2. So we were able to take this negative 6x cubed minus 17x plus 63x minus 10. I'll write it down just in case. Sometimes I like to reiterate. So we can take that equation and we can right away show that we have x minus 2 as a factor. Now earlier, we also came up with the factorization using synthetic division. So I'll let you watch the previous video so that you get a better idea. But we ended up, after all of this, and I'll go with this, we use synthetic division. But we were able to take a quadratic factor and break it down so that we had 2 linear factors. So we end up having, just so that we skipped a few steps here, but you can rewatch the other video, this factorization ended up being, what do we have, negative 1 times x minus 2 times x plus 5 times 6x minus 1. And that was all equal to 0. So now that you have linear factors, this is the valuable part. You could actually solve by setting each factor equal to 0. So that's why we wanted to worry about factoring these. So if I finish that off with you, keep in mind, this negative 1 factor does not affect anything. It is a constant factor. Technically, it divides out. If you wanted to ignore it, you can, because it does not have an x in it. It disappears for the most part. So really what we're looking for is x minus 2 equals 0, or x plus 5 equals 0, or 6x minus 1 equals 0. Now we already knew that 2 was a root, so we already had that down, but we did not know the other ones. So we have x equals 2, x equals negative 5, And a little bit of work here. We have 6x equals +1, or x equals 1/6. So there's 3 roots to this polynomial equation. So you could definitely circle each of those answers if you'd like. Or sometimes you will see it written in set roster notation where the solution, oh, maybe I'll spell out solution. You are formally on a video. You'll write out those solutions. Those are your roots, -5, 1/6, and 2. In any order you'd like, of course. But remember, those are roots, zeros, or x-intercepts, or in other words, solutions to the polynomial equation p of x equals 0. So that would be kind of why we're interested in using synthetic division to factor. So you might be questioning, well, how do I factor it if I don't know a root already? And that's a good question. And that just keeps you hanging on for more. I'll show you in a few examples.